Recording in progress.
Hello. Is the audio good? Can you guys hear me? Yeah. So, thank you. So, hello everyone. Welcome to Recitation 10 on Attention, Machine Translation, and LAS. And thanks for coming here so early today. And thanks everyone for joining on Zoom. So, moving on to the problem that we are looking at, it's the sequence to sequence conversion problem, such as the one that you came across in homework 3 part 2, where you would basically have like an input sequence. In this example shown here, the input sequence can be anything like a sentence or an audio signal, and the output is also a sequence. It is not necessary that the input and the output should be time or order synchronous, as you might have seen before. So as an example of not having order synchrony is the second example which you see on the screen, in which you translate an English sentence, I ate an apple, to a German sentence, Ich habe einen Apfel gegessen. So here, if you notice, ate is actually the second word in the English sentence. But when it comes to German, I think it's a combination of like habe and gegessen, which is not necessarily in the same position that it occurred in the input sequence. So this is one sort of discrepancy that we need to deal with in our modeling approach so that our translation is correct. So for an example, if here we were just to output the word gegessen when we encounter, as soon as we encountered it would be a wrong translation. Like it would not make grammatical sense. So these are the problems that we should be keeping in mind when we face like sequence to sequence conversions. Now coming to the language models, which we have already seen earlier in our lectures. So you have a bunch of words given to you in the vocabulary. You might have words in the range of thousands or tens of thousands. So you usually represent each word as a one-hot vector. So if you're trying to represent the first word in a one-hot vector, you would just have like a 1 followed by a bunch of zeros. Similarly, like if you are looking at a word which is basically you're representing the second word. So it's going to be like a 0, 1 followed by a bunch of zeros. So this is, as you see, a very sparse representation, right? So in order to make it a little dense and to decrease the amount of features which you are using for your representation, you project it to a lower dimensional feature space with the projection matrix or the projection layer, which you can see here. So this is basically like a word embedding. This is basically a word embedding. You pass the word embedding to your language model, and then it actually generates an output for each time step. So these green boxes are the language models, and you can actually have like a lot of layers or like multiple layers of LSTMs, GRUs, and so on. So that's like basically how a language model works. You take a one-hot vector, W1, you project it, you get the word embedding, you pass it through the sequence model, and then you finally get the outputs. And like which are translated, or it just depends on whatever application that you're looking at. So a note on the beginnings and the ends when it comes to language models. A sentence will only be considered to be complete if it has like a start of sequence and an end of sequence token attached to it. From the previous lectures and also in homework 3, you now know that these two tokens play important roles in the encoder and decoder steps of the architecture. So basically, you're trying to predict sentences from one language to another. And in the case of, say, take for example, in the case of a poem or something like that, you actually need a pretty solid start to the sentence and an end to the sentence. But in the example like you see here, 4, score, and 8, it's not really clear whether this occurs at the beginning of the sentence, in the middle of the sentence, or at the end of the sentence. So just as an example, you see here that the first example here does not have a start of sequence and end of sequence, so it's like the middle of the sentence. This begins with a start of sequence token, so it represents the beginning fragment or the starting of the sentence, and similarly for the end of the sentence. So we'll be using SOS and EOS more importantly for like the generation portion of the language model. So returning to our problem that we described earlier, a sequence that like x1 dot 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 xn, which is represented by this input sequence in the example we described earlier, it goes in as one and it comes out as a different sequence. So there is no expected synchrony between the input and the output. And so this is actually the problem that we are looking at. Now let's try to build up from a simple way to a current best way to model this problem. So this is what you see here is basically like a delayed sequence to sequence conversion. So what you're essentially seeing here is an encoder-decoder architecture. So these pink blocks represent your encoder, and these blue blocks represent your decoder. The green blocks here are the hidden states at any given time step. So you first pass your input through the encoder and generate its corresponding hidden states. And once you have passed the entire input uh, at each time step, you can just try to hope that this encodes the entire input sequence in this particular hidden layer right here where it ends with enough information. So this hidden state representation, you can take it as the representation of the entire output sequence. And now you can use this to begin your decoding, which happens starting from the next time step in the blue blocks. Uh, so again, like basically what you're doing is you're passing the inputs together to the sequence model, but you don't start predicting the output immediately. You just get the summary of the output, or like I said, the final hidden state representation, and then you try to build on top of this summary to get the output. So just like as a very trivial example, you can actually imagine the case of a language translator, right? Like you're speaking a different language, in order to make them understand and translate it into another language, you sort of have to give them like the overall context, and you have to let them know the entire deal before they translate it to like a different language sentence. So coming to the simple translation model, just to make it more clear, this is how our architecture will look like. So you'll start off with an initial hidden state, and you pass your English inputs one by one to the encoder. The red block here will contain the entire hidden representation of the entire input sequence. And the last input to that will be the end of the sequence token, the EOS token, which is essentially an indication to just start with the decoding process. And at the next time step, now you'll have the SOS token as your input, and you're passing the encoder hidden state to the decoder. And then together, this will give you like the output probability distribution over the German vocabulary. So like in the previous slide, we saw the case where there is like a single hidden layer. But the same discussion, we can generalize it to more layers. So let's say you're working with LSTMs and you have multiple LSTM layers. You can add multiple LSTM layers, you can make them bidirectional, and so on and so forth. So the overall concept of the architecture would remain the same, and this is just like a very simple illustration of that. And this is a diagram just to demarcate our encoder and decoder portions that I spoke about earlier. Yeah, now coming to generating an input from the net. In the decoder, you start off with the SOS token and the last hidden state from the encoder. As you can see here, this red box and the SOS token. And you generate a probability distribution over your German vocab. So what you're basically doing here is, at each time step in the output, you'll have a probability distribution among all the classes or words that are present in the language model. So you actually try to select the most probable output, and you try to give it to the next time step, like which you can see here, the ish has been passed right here. So for a typical generation process, you continue to do it until you encounter the end of sequence token, which is where you essentially stop the process. Um, Moving on to how you are training the language models, in the forward pass, it's basically straightforward. You just have an encoder which gives you the summary or the final hidden state representation, and with that, you generate the outputs. and you generate like the predicted outputs. Coming to the backward pass, what you do here is, since at the decoding time step, you have a prediction as to what the model thinks the word should be right now. Uh, and you also have the actual ground truth with you. So basically, like you have these predictions y0, y1, y2 at the decoding time steps, and you have the corresponding desired output called by the dt at those time step. You can calculate a divergence between these two, okay? And once you, which is basically, it can be anything. It can be KL divergence or a cross entropy loss, whatever. But something that has become a standard practice here is, instead of calculating divergence between all of these y's and all of the dt's, we can just randomly select one y and one dt pair from the entire decoded outputs, calculate the loss between just this single pair, and then back propagate it instead of like doing it for all the pairs of sequences. So this is just to make your process efficient. Even if you do it for all the pair of sequences, it's fine. It's just going to be a little like computationally inefficient. But in order to just understand what is happening in this given diagram a little better, you calculate the divergence between the ground truth and the predicted word at the fourth time step here, say the y4. And then this divergence is actually passed across all the time steps. The reason why you're doing this is, like as you see in the fourth time step in the decoder, it has actually seen all the inputs that have been given so far. So any small change in either one of these will actually affect the computation of divergence like overall over here. So basically how you calculate the gradient flow goes in this manner. So if it doesn't actually affect the gradient flow, you don't really have to update those weights, which is why the method which I mentioned before, the computationally efficient method, it kind of, yeah, works better. Moving on to machine translation example, Mohammed will take it forward from here. Um,
Hello, good afternoon. Good morning. Can you see my screen?
yes, we can. Can you like present it in the slideshow mode, please?
Huh?
Can you change the mode to slideshow? Yeah, thank you.
Yeah. So, as she has explained, uh, with RNNs and strictly neural networks, this visualization shows what the model generally learns. So it learns to cluster the different inputs based on their meaning. So as you can see here, Mary admires John. Mary is in love with John. Those two, you can see that close together as they have similar meaning. And then John admires Mary, and John is in love with Mary are also clustered. And this one, Mary respects John, which has no similar meaning with the rest, is on its own. And then you have John respects Mary here. So this is generally what is the sequence to sequence learning with neural networks results. So moving on obviously there's a problem with the strategy that she just explained, in that we expect the last hidden state to carry all the information of all the inputs. Imagine if you have an input, like if you're using ChatGPT, which I think most of you guys will be using, you write a whole paragraph and then you expect the last hidden state to carry all the information for all the inputs, all the words and characters that you have inputted. So this is a problem that has been tackled in the literature. So we're going to explore some of the solutions. So simply what we could do is just take an average of all the hidden states from all the words or whatever token that they're using, which could be characters or words. Then we can use all the hidden states from the entire input and just make an average. And then we can use that average to generate the output at each time step. But there's a problem with this approach as well. So the average assumes that each word in the input has the same impact on the output at each time step. So an example is given here. I cannot speak Dutch, so I'll just believe what this is saying. So from what we are trying to translate here, I ate an apple. I corresponds more to the word here, ICH, than all the other words in the output. But if we just simply take an average, we are assuming that all the words play the same role in outputting ICH and also in outputting HABE and all the other words. So this is also an undesirable problem that we want to solve. So another thing that we can do is use all the inputs from the hidden states, but we weight them differently. So each hidden state is going to be weighted differently based on what we are trying to output, at which time step we are. So if we are going to be outputting ICH, which is time step 1, we want to I here to have a greater weight than 8 and apple and the end of sequence symbol. So this is one of the ways that we want to tackle all those problems. So how do we do this? These are generally called attention models, right? So the weights are obviously we want the weights to be dynamic. We want them to depend on at which time step we are dealing with in the output, right? To be able to get a dynamic weight that will be used to rate the different input hidden states based on their importance in generating the output. So here we summarize the computation and how we achieve this. So we just introduce a function here, G, and G is a function of the hidden state and the output time step that we are doing. So another property that we want this weight vector to have is that we want it to sum to 1. So we want it to be a probability distribution over the input hidden states, right? So that they will be weighted according to their importance in generating the specific output. So what is G? There are multiple candidates, obviously, for G. So you can see here, we can take G to just be the dot product between the hidden state and the hidden state in the input and the hidden state in the output. Or we can project the hidden state, so we can add a learnable weight matrix that will project the hidden state and then take their dot product. These are also other examples. You can see we can also make it as complex as an MLP, right? So how would you generally use this mechanism, this attention mechanism, to generate or to translate, to do machine translation? As she has already presented, in a similar way, you would feed your inputs into a neural network, usually a recurrent neural network, and then you will, that is usually called the encoder, which will produce hidden states for all the input sequences. And then you initialize your hidden states in the output layer, and that will also be a recurrent neural network. So you can initialize the hidden state in the output as 0, or you can learn it. Another alternative is to just take the final hidden state in your input sequence as the initial hidden state in your output sequence. And then, as we have discussed, you would generate attention contexts, and each of those contexts will be generated dynamically, as we discussed. At each output time step, we will use a different weight matrix, a weight vector, to weight the hidden states differently for that particular output state. And then the output will then be passed to the next time step to generate the next output as well. And for that second one, we'll compute a different context using a different weight vector. So we have this. So you continue this process till you hit the end of sequence token, then you know that you have reached the end of your generation process, and you terminate. So there's a slight modification of what we've just discussed that is widely used, and is also the attention mechanism that is used in the popular transformer models. So instead of just using the hidden states from the input sequences and the hidden states from the output sequences, we now project this thing. We project the output hidden states into queries. So at each output time step, we're going to have a query vector, and at each input hidden state, we are going to have 2 representations, a key and a value. So you can look at this as just projections. So we just project the hidden states, basically using weight matrices, which will be learnable, right? So the encoder is going to output explicit key and value at each input time, and the decoder is going to output explicit query at each output time. The weight function here too has to be dynamic, obviously, and it is going to now be a function of the key from the input or the encoder side, because the encoder outputs the key and the value, and the decoder outputs we get the query from the decoder. So the weight is going to be a function of the key and the query. And then the actual context that we are going to finally use is going to be a weighted sum of the value which was gotten from the input sequences, that's the encoder. So this is an example of a special case where we just set the key and the value as hidden state and the query as the hidden state of the output, which was what we initially had in the previous slides. So what does the attention weights learn? So as like we motivated the idea, we expected, and it sure does learn that. What is learned is to be able to attend to the more important input tokens at each output time step. At each step of the generation process, it learns to attend to the more relevant and more important positions in the input, which is what we want. So there have been extensions of this, which is obviously used in the transformer model, which is multi-headed. So it's not very different. Instead of having one key and value pair for each hidden state, we can have 2, 3, or multiple pairs of key and values. And then we will have pairs of queries also from the decoder, the hidden state. And then we will do the exact same thing with each of those pairs separately. And then we will use all the results from all of these in our decode process, in a process of outputting the sentence. So this is desired also an advantage because now with multiple heads, remember each head, like we introduced it here, this was one head. So it is going to learn to focus on certain positions in the input when outputting at different time steps. Now with multiple heads, it's going to have more capacity. Each of those heads can choose to attend to different parts of the input as we are generating our output. So some tricks when we are training this. So remember we said when we are generating the output, we pass in the context, which are computed from the attention. Then we pass in the previously generated sequence token. So for the generation of HABE, we would have passed the token that was generated for ICH. So, but as we all know, when we are training these models, they are not perfect. So they can generate wrong tokens at different time steps. But now if it generates a wrong token, it means we are going to be passing this wrong token to the next time step, and the whole network can end up just generating meaningless sentences or words. So how do we tackle this? One of the tricks that we can use is instead of passing the generated token, we can pass in the actual or the true label, the ground truth token to the next generation at the next time step. So this is called teacher forcing. So at the end of it all, as you can see here in this visualization, the attention, how the attention mechanism works. You can see the bright colors are showing more importance. So the two sentences here, you can see the model is able to highlight the most important positions in the input at the generation of an output, which looks pretty cool. It is mostly linear because again, the order of the words in the two sentences, the two sentences from the two languages uh, mostly relative. So here is an example of sentiment analysis, and the words in yellow are like the highlighted ones by the attention mechanism. So you can see it is highlighting that this part of the sentence is what makes this a positive sentiment. And if you read it, you can affirm that. And here, which is a negative one, you can see where the parts where it highlighted the users, where the user is given its negative sentiment. Here also, attention models have also been used in images, doesn't only work on text. Here you can see from my image, it is generating a caption. And when it was generating the caption frisbee, the attention model highlighted the frisbee, the location of the frisbee in the image, which is pretty cool. And you can see here when it was generating the word dog, the dog in the picture was highlighted, and so on and so forth. So now we go to last, which you will be implementing in homework 4, which uses the attention mechanism. It has an encoder and decoder. The encoder is basically called the listener here, which basically listens to the spectral values or features as your input, and it generates hidden state, which is passed to an attend and spell. But an important step that happens in the listen is that the input sequence could be very much larger than the length of the output sequence. So it takes advantage of this. And in the input, in the listen, where it generates the hidden states, it reduces the sequence length of the hidden states. As you can see here, the hidden states are H up to U, which is sequence, and that would generally be less than or equal to the total sequence that was received from the input. But also, you will face this in your homework. You will need to take care of not reducing this to a point that it is lower than the sequence length of the output. So with those hidden states, as we have discussed, you can see the attention context here. It takes in the hidden states from the output sequence, and the H is the hidden states from the input sequence. You generate your context from that, and then you generate the hidden state for the next sequence, and use that to generate a distribution over the vocabulary for the output sequence. So that is the end of this recitation. Over to you, teacher.
Yeah, I think that's the end of our recitation. If you have any doubts, please feel free to go ahead and ask them, or the ones on Zoom can drop it on the chat.
Thank you.
No worries. Thank you for coming at 8 a.m.
Will you be taking questions on homework 3?
Homework 3 is over, right? Homework 4.
I mean, yeah, but
Oh, Slack days.
Yeah.
Yeah, sure.
yeah,
I can take homework 3 for now.
yeah. Yes. Something on the private school,
Okay. Is it too high, like 6.1? So if your weighted score is like 0.6 into private plus, I mean 0.6 into private plus 0.4 into public is less than 6, you will check that.
Is it the end of the recitation?
Yes, as well. I don't know. I'm not hearing them over there. Do you have any questions? You guys have any questions? You can ask us.
I don't even know where to start, so I'm just lost.
Oh, you joined late or what?
How many years?
I'm lost from all this. I don't even know. I think from the first line.
oh, but I was mainly confused by I used to come here.
But I didn't get the part where you're talking about. Is it a teacher forcing? Where you were saying you feed the input rather, or is it the output? I wasn't getting that side because it didn't look any different.
Take care of
The teacher force it.
the thing here.
Yeah.
Yeah. So you were saying Okay, is it
Yeah.
the EI over there?
Want to use dropout and
Yes. So you can see here. Usually, what do we do when we are choosing the correct uh,
batch norm.
token that was generated here? We take the maximum, the most probable, right? So we just sample from the distribution that was generated at this time step over the tokens. So we take the most probable as what the model thinks is the correct token for this time step. But remember, the next time step needs that token to be able to continue the generation process. So now, if that token is wrong, it means the next time step will be relying on wrong information or on incorrect information. So we might end up just generating rubbish all throughout. So how do we tackle this? Remember, during training, we have ground truth levels. So instead of passing this, which the model thinks is correct, we pass the correct one. So we force the model. So the teacher is forcing the model to do the right thing.
Oh, that's really good.
Richard?
Okay. Not so clear because if you look at it, the output is forcing. Okay, so which one is the ground truth? The ground truth is it not the you see the colored text at the top,
Yes.
right? And then where your mouse is. So is that a correct one or that's what is generated by the model?
So that's the correct one.
Yeah. So
Yeah.
because it seems that the correct one is rather being fed down. If you look at the bottom, it's like that each have like this is the same thing, right? It's the
So
same. Is the
at
correct
the
one is rather being fed.
at the bottom here, you can see this is it starts. We don't know the output.
Yeah.
You can see. Yes. So it is
So
not
from the
the one that is
diagram,
being fed. Mhm.
it looks like instead of feeding the is it ironing, it's rather feeding the EIN. Not
Yes. So that is what would happen normally in training, right? Because we don't pass the correct answers to the model during training. We just use it to compute the divergence, right?
okay.
Right? So for here we say we need to tweak that a little bit. Usually we don't pass the correct answer until at the end, then we compute the divergence and then uh, pass back the derivatives. But here we say we could also input the correct answer during the training process, not wait up to the end.
All right. Thanks for explaining.
I guess that's all. Thank you guys for coming and good luck.